¿Se está recibiendo el micrófono? Sí. Ahí está, ¿verdad? No te da el... Ahí está.
Okay, the next speaker is Darian Reyes Fernandez. He recently obtained his PhD degree from Instituto Tecnológico de Tijuana, and he's going to present the talk Vhdl by MOEA, a tool for multi-objective optimization in high-level synthesis. So please welcome Darian, please.
Good morning. As Victor said, my name is Darian Reyes Fernandez de Burnes, and my PhD dissertation was last Monday, just 3 days ago. And here we are going to present the last chapter of the thesis. It's a tool approach for multi-objective optimization in high-level synthesis for SPA device. It is entitled Vhdl by MOEA. My advisor is the researcher Yamil Maldonado, is here with us. This is the presentation overview. First of all, we are going to see the SPA device architecture, some methodologies, and the state of the art of the high-level synthesis tools for this kind of device, and some limitations that we identified. Next, our system proposal, the methodology of our system proposal, and next, we are going to see details about the 4 modules that contains the software tool. The software tool that we developed was developed modularly, and it contains the interface module, C code compilation module, multi-objective optimization module, and Vhdl code generation module. Next, we are going to see an online demonstration in a server, an instance installed in a server in the Instituto Tecnológico de Tijuana, in our laboratory there. And to finish, the conclusion and future work. Free program array, or FPGA, is an integrated circuit that which could be programmed in situ by a designer after manufacturing. One of the most advantages of this device is that it has high potential for parallelization. This is the general architecture. It contains configurable logic blocks, input, output blocks, and the interconnections. And this figure at the right is the real FPGA, the dealing basis 3 RTX7 FPGA board. It is of Xilinx. Xilinx is one of the most important companies that produce the FPGA device in the world. Intentionally, we present this device here because following in experiments that we are going to present here, we use this device for some experiments. Then, the FPGA design is generally specified by hardware description language. It could be Vhdl or Verilog. But when this design is complex, for example, a fuzzy system controller or neural network, it's difficult for the designer to create the Vhdl or Verilog code optimized for an SPA device. Then exists another methodology called high-level synthesis that allows designing at a higher level of abstraction, which leads to increased productivity. There are optimization opportunities there. The input in high-level synthesis methodology is a behavioral description as software in common language like C, C++, C#, Simulink models, and so on. This is a Euler diagram with different knowledge fields. At the left, we get in green the optimization methods, and as subset the multi-objective optimization method. And at the right, we have the methodologies to implement designers the methodologies to design FPGA device and three kinds of synthesis. High-level synthesis have higher level of abstraction at algorithmic level. Next, logic synthesis on logic gate level, and finally the layout synthesis in electrical and layout level. Then, our research is focused here, applying multi-objective optimization methods in high-level synthesis. We built this table that contains the state-of-the-art of software tools that perform high-level synthesis for FPGA devices. And here we identify aspects of interest. For example, C is most of the common language to get the input, and Vhdl is the one of the most used language to get the output. Only 6 of them are for academic proposal, and anyone develop the multi-objective optimization like we are going to develop in our tool. We're going to see next how our tool perform the high-level synthesis with multi-objective optimization algorithms. Here it is Vhdl high-level synthesis is the software tool of Xilinx, and Intel high-level synthesis is the software tool for Intel. Remember that Intel bought Altera company. Then we use Vhdl high-level synthesis to develop a depth analysis. For example, to study the Vhdl structure in finite state machine, the finite state machine structure. Okay, we identify some limitations focusing on the multi-objective optimization in this state-of-the-art table. Okay, for example, little possibility of variation of the optimization algorithms and their parameters. A few charts about the optimization process, which it is necessary to seek detail of interest. No access to a Pareto from. This is important because it's important that the designer can choose which solution will be implemented in the device. And finally, the optimization process is usually done on client side. It is better on server side with high computing and parallelization potential, because the multi-objective optimization algorithms are iterative algorithms. It's better if this kind of algorithm runs on a server side. Okay, this is the stage of our methodology, of our high-level synthesis methodology. First, we get the behavioral description in C code. Then it is the C code. It is compiled into data flow graph of DFG. This is an intermediate structure. Then the multi-objective evolutionary algorithms, or MOIAs, runs over the data flow graph. Instead, a single solution, the multi-objective evolutionary algorithms give a result Pareto from approximation. Then the designer can choose which solution he wants to convert to Vhdl code of this set of solutions, the Pareto from approximation. Then the Vhdl code is the input of Xilinx Vhdl 2019, and it is in charge of implement the designer in the device. Okay. Then, as mentioned in the overview, our system contains 4 main modules. This is the first one, the interface module. It has a model view controller architecture, and the control component is in charge of invoke and read results with the 3 main modules in C++. Okay, the C code compilation module, the multi-objective optimization module, and the Vhdl code generation module. Then, these 3 main modules, it is represented here in this general diagram. We get the input in C, then the compilation is done, the multi-objective optimization and the basic scheduling is done. The basic scheduling is just to compare how the multi-objective optimization algorithms, only for comparisons with the multi-objective optimization algorithm to measure the optimization. Okay. For that reason, this module generates a basic scheduling too, and the free one is in charge to the conversion from the schedule DFG to Vhdl code type finite state machine, and the result, the output is Vhdl code. Okay. Then we are going to see an example of the compilation, how the compilation module works. This is a C code, very simple with summation and multiplication. Then the lexic analysis is done with the help of Flex library in C++. The token is sent to the syntactic analysis with the Bison library, and the abstract syntactic tree is created, and to get the DFG only with a rotation and a little transformation, we get it. Okay. Then the multi-objective optimization module contains these 3 algorithms, NNCI2, NNCI3, and SPIA2. In previous work, we demonstrate that these algorithms perform well results for this problem, and the basic schedule is here as soon as possible, as late as possible, and random scheduling. Okay, we have 3 objective functions. Delay is the necessary step or closed cycle in the SPEA. Occupied area is the sum of occupied functional units plus occupied registers, and the dissipated power is the dissipated power in the SPEA when perform the design operations. And this is the main equation of the multi-objective optimization when all objective functions are of minimization, where D is the decision space and X is the vector of variable space of decision variables. And on the other side is the objective space, is the result of projecting F in D. Okay. And finally, the conversion of the schedule DFG to Vhdl code, and here we get a simple DFG with multiplication and sums. Okay, we are going to divide the operation in states because we are going to generate a finite state machine Vhdl code. Then it means that these operations we are going to is going to run in the device currently. Okay. In this example, we have 4 states, and this is the state diagram example. Okay. Our tool use these technologies for the front end, and the backend is a web-based interface. And the backend, we use a database to save some data about the optimization process, the evolutionary optimization process. And in the backend, all the main models in the backend are written in C++ language to perform in a higher execution time. Okay, we are going to see here a demonstration in a video. This is the link to access free to the tool, and this is the home of the tool, and the help section we get some examples, some behavioral description examples. One of them we are going to use here with this is C code. For that reason, we use pointers to get the results here as parameters. We wrote optimization title and select the behavioral description here. Next, the designer can see the data flow graph and its features, the nodes, the edge, detail of interest here. The darker node is inputs and outputs, and lighter node are operations. For example, this support, and here we can see the DFG structure in GraphML viewer. Okay. Next, we define the multi-objective optimization parameters. First, we choose which algorithm we are going to is in charge of develop the optimization, and the evolutionary parameters, for example, population size, generations, and crossover probability and mutation probability. We can set all this, and immediately the objective space is shown. This is a very, very simple experiment. The lighter points here are the random initial population, and the darker points are the populations on generations. The tool asks for basic information, and finally, the designer can download the Vhdl code optimized by the algorithm. Okay, and to make comparisons, the basic scheduling can download too. This is the Vhdl code as result. We can see it here in the web. Okay. We use a Citedi logic for inputs and outputs to. It's important to mention that here we are going to insert this code in a silence device, but we develop experiments with Altera Quartus 2. Okay, this is another example, a little more complex, to see an objective, the optimization in the objective space. Okay, see that we had several expressions here. The DFG is more complex too. Okay, 89 nodes and more than 100 edge. We select here the SPIA2 algorithm and 100 population size, 100 of generations. Okay. This optimization spent more than 5 minutes, but we are going to accelerate the video in the 10th generation, I think. And here we can see the population generation in darker. Okay, this is a 3D space because we have 3 objective functions. Okay, power, area, and delay, as mentioned previously. Okay, I accelerate here the video, and generation shows here, and we got the Pareto from approximation here. The designer can choose which solution he wants to implement in the device, okay? And the estimations is shown here. He has the option of select the balanced solution and a random solution too, okay? Okay, and the same, we have the Vhdl here, okay? Then, it is a fragment of Vhdl code. This is 2 states, and for example, the reutilization of the register 2 is shown here. This reutilization is made by the optimization process, okay? Then we check during the simulation in the Silence Vivado tool with the waveform viewer. We can check if the perform of this circuit is the same that we define the C code at the beginning. No? Okay, the objective functions in this tool, in the Silence Vivado, we can match, for example, the delay, the critical path here, with the delay estimation of the algorithm. Okay. Then this Vhdl code can be implemented in the SPA device, and here this is the board that showed at the beginning as an example. Okay. As conclusion, the state-of-the-art of high-level synthesis tool for SPA devices was researched, and limitation was identified. Subsequently, a software tool was developed to perform multi-objective optimization in high-level synthesis. The interface web-based client-server taking advantage of the computer power of a server with high performance. The system was designed modularly and composed for 4 modules. Interface wrote in Python with the Django framework, model view controller architecture, then C code compilation in C++, multi-objective optimization in C++, and Vhdl code generation in C++. As future work, first, input expression in C language is very limited right now. For that reason, it's necessary to allow more expression, and for this, the intermediate structure have to use, for example, here in this reference. To optimize more than 3 objective functions, for example, temperature, interconnection, digital noise, security, and reliability. Consequently, in order to visualize the objective space, it's necessary to map the m-dimensional space in 3-dimensional radial chart while preserving the solution relative location. Okay, and to employ the Django WebSocket Redis, for example, to achieve that the optimization can done with the web interface being active in the browser, because right now, if you close the browser, the optimization is broke. Okay. Then incorporate indicator-based evolutionary algorithm (IVE). In previous work, we demonstrate that this algorithm perform well results for this problem. Finally, integrate the system with a software as a service like Amazon through a application programming interface API. This could allow linking service to have implemented the Vhdl code in SPA using the cloud on the floor. Okay. Thank you very much.
Thank you for the talk. Question for the speaker, please. Anyone have one? Okay, I have one. Oh, there's anyone? Oh, sorry.
Just one question. What other objective functions, Darian, could you optimize besides just those?
Yes.
First, why you choose those three and which others could you optimize?
Okay, we developed the state-of-the-art study, and we identified that the delay and occupied area and dissipation power are the most used and more important objective functions. For that reason, for that work, we use 3 objective functions, but we identified that authors in different places in the world optimize independently temperature, interconnection, digital noise, security, and reliability. And this is a research opportunity because we can focus this problem as a many objective optimization problem.
Another question? Okay. You are optimizing right now the delay,
Yes.
the power consumption,
Yes.
and memory.
Yes.
When you optimize all these criteria, the accuracy of the data is not affected by optimizing these
No.
criteria?
No, the behavior of the circuit is intact. Yes.
Okay.
It not affect the computation of the operation in the circuit.
Okay.
For example, in this example, we show arithmetic and logic operations that we get as input, and the output, these arithmetic and logic operations in the real SPA here, we check that are the same,
Okay.
exactly the same. No problem with it.
Thank you. Okay. Another question? Okay. Well, so please thank the speaker again.
Thanks. Sí.